Hey. So I will be talking about ML infrastructure at Netflix. Hopefully that's okay. I mean, I'm pretty sure that like Lyft has similar problems as well. And actually, like the previous presentation had a really good segue to mine, which was that like 80% of the work is in the infrastructure. So, like where are the slides? Oh, well, anyways. So yes, so I'm Ville. I work at Netflix. I work on ML infrastructure. And by the way, I mean, one disclaimer is that like most of you, when I say machine learning and Netflix in the same sentence, might be thinking about recommendations. Unfortunately, this talk is not going to be about recommendations. So I mean, there's no chance for you to leave. I mean, looking at the crowd, so it doesn't like matter much. So anyway, so what I will be talking about today is actually like related to the fact that although Netflix has been doing recommendations for the longest time, so you know that like when you go, thank you.
Is that good?
Let's see. Actually, like, can I go? Yes, that's me. So yeah, so about Netflix ML infrastructure. So yes, so you know that like Netflix has been doing recommendations, TV show, movie recommendations, like for a long time. So you go to netflix.com, you see all those TV shows and movies being recommended to you. So that has been going on for a long time. Now the interesting fact is that about 3 years ago, there was the realization that an increasing number of ML use cases at Netflix are actually outside recommendations. And I think that there are like two reasons for this. One reason is that like the Netflix has been going really global. So Netflix is now pretty much in all countries in the world except China. And the second reason is that like Netflix has started producing its own content. So as you also might have noticed, there are these Netflix originals all over Netflix. And like it turns out that like producing TV shows and movies is both hard and expensive. And we kind of realized that like for the long-term survival of the company, it's super, super important that we get really smart about this. And one problem is that like we are kind of doing this at a larger scale than any other company ever in the history of humankind, or at least TV production. So we really like want to do this well. So there are tens and tens of machine learning problems that we are doing these days outside recommendations. So we are applying NLP, for instance, to understand this, the kind of how likely it is that a movie or a TV show is going to be popular just by looking at the script. We can do that like using NLP. Of course, it's not always fully accurate, but that's something that we are trying to do. Also, like during the production of a TV show or a movie, we can actually apply machine learning in optimizing the whole production. So as you can imagine, like just like organizing this like a large-scale productions is a big undertaking, and we can apply machine learning in like just making sure that the actors are at the right place at the right time and so forth. And now we literally have tens of use cases like this. And now, well, I work on the machine learning infrastructure. And now you can imagine that the problem we have is that we have so many different kinds of use cases. So we have NLP, we have a computer vision, we have more classical statistics. And the question becomes that is there anything in common that we can provide for all these use cases? So it is one thing to build like really, really good infrastructure, for instance, for the dispatch problem or like the recommendations problem at Netflix. But if the task is to help people working, hundreds of people like working on all these different problems, how you do it? Well, now, one way of solving this problem is that you look at like what data scientists are actually doing in their daily life. So, I mean, taking a very human-centric approach in that sense. And I know that many of you are data scientists, so I'm sure that like many of these things will resonate with you. And now the first thing that I want to mention, and like, by the way, these are real quotes like from the real life data science happening at Netflix. So this is one example like related to the software architecture. So there was a data scientist who was like working on this project, like where you had the situation that you build a model and the next day's model depending on the previous day's model, and also like for the new data that was coming in. So you now have the situation that you have both a model as well as new data coming in, and like you want to build a new model based on that. And the question is that like how do you organize such a thing? How do you go about building the software? And now just to kind of give you a bit bigger context that like what is like data science really about these days? So I mean, I think that the previous presentation was really like one of the most fascinating use cases like for machine learning and optimization, and like much of it is actually software engineering. So now, like if you think of data scientists at Netflix, and like we are like really special maybe in the sense that we give a lot of autonomy like for our data scientists. On the one hand, like we want them to take the project all the way from the experimentation stage all the way to the production. So that's one axis. Then on the other hand, like we want them to kind of cover the whole space like from getting the upstream data all the way to connecting the results to some other business systems. So another challenge is that unfortunately, like to big disappointment to all of you, like machine learning doesn't really have any value in isolation. It needs to be connected to some business processes. And like how you do that connection is oftentimes non-trivial. So there's a ton of software engineering in this work. And like the thing is that like we have amazing people working on data science, but they are not always software engineers. So architecture, like software engineering, like remains a big problem in these pipelines. Another one, like going down the line, like what's really important for us is that at some point we realized that there's absolutely no point for us to start re-implementing any of the models, any of the modeling frameworks, which since like you can get all these things off the shelf today. So there are things like TensorFlow and Keras and scikit-learn, XGBoost are amazing things out there. But by using these off-the-shelf libraries, which give you a ton of leverage, you expose yourself to an amazing amount of entropy out there. And this is an example that we had, like there happens to be this Python package called fancy impute. Fancy impute depends on this Python library called cvxpy, which is a convex optimization package. What they did is that they released a broken version that broke fancy impute that then like broke one of our like production pipelines. And now, well, I mean, people who here have built these machine learning pipelines before, like, might think that, well, I mean, like, of course, I mean, you are supposed to at least pin the versions or maybe create the Docker containers or something. And well, I mean, it might be a challenge if, like, the fancy impute doesn't exactly pin the version of cvxpy, and it's complicated. It's really honestly complicated how you do these things right. Another big one is data access. So, like we actually went around at some point, like talking to all data scientists at the company, asking like, what's the biggest problem for you as a data scientist at Netflix? And we were expecting that people might complain that, well, I mean, they need to build larger scale models and they need distributed TensorFlow or something of that sort. And unfortunately, like that never happened. No one said that. People were in 95% of cases complaining about data discovery or data access. How do you like find the data you need for your models and how do you access it fast? And now Netflix has really pretty mature like data warehouse. We use Presto, we use Spark, we use all kinds of things. And the typical way to get the data is by writing SQL. And that's all good and fine in many cases. Unfortunately, in some cases, that can become a bottleneck in your project. So it can be that like just like running the query takes something in the order of like tens of minutes, and it's just like kind of makes it harder to iterate things fast. So that's another thing that like we really like would like to solve. Then like there's the obvious one, which is scalability. So now in this case, there was a project like where they wanted to train thousands of models, and they wanted to do hundreds of models per country. So that's like tens of thousands of models. And on top of that, they wanted to do hyperparameter search. So now you can imagine that you are building potentially tens of thousands of models. And again, now you might think that, well, I mean, given a suitable like distributed system, container management system, you can just do it. And yes, you can. But how to do it well is a non-trivial problem. And then finally, imagine that like you have gone through all these steps. So you have solved the question that, okay, how do I structure my code base? Then like you have thought about that, okay, so what kind of a modeling libraries I use, what kind of dependencies I need. And then you figure out maybe how to deal with scalability. You figure out how to deal with data access. Then finally, you deploy your model to production. And now what happens is that you never deploy a machine learning model only once. It's a continuous process. It's like a relationship. Now we are kind of dependent on this thing like forever. And like what happened in this one case is that like we had a project that was like running for a time like quite reliably, and then it started failing. And now in this case, the data scientists had a good guess, which was that like as we are getting like more members, as we are getting more accounts, like we are just like running out of memory because we can't handle all the data, which was kind of easy to see in this case, but oftentimes the problems might be more subtle. And this is kind of an interesting study that we made at one point, looking at the actual friction experienced by data scientists in their daily life at Netflix. And now this is kind of summarizing what I just said. Like maybe not surprisingly, maybe surprisingly, I mean like one of the biggest like a source of question and friction was actually just related to how do I do software engineering? How do I architect my code in a good way? The second one was like, how do I operate my models? How do I deal with these like errors that happen? How do I deal with all kinds of entropy that like kind of sneaks in from the outside world? How do I deal with dependencies? I mean, like I used to be using like a TensorFlow 1.14. Now I want to test TensorFlow like a 2.0 RC, and like how do I do it? Or like when things fail, like debugging, like even when you are experimenting something and things fail, I mean, like how do I interpret the errors? How do I deploy these things? And like when I say deployment, remember that like we are dealing with tens of different use cases. So there isn't like one like system where we are deploying, but there are literally tons of different business systems. In some cases, we want to push results to a dashboard. In other cases, they might be going to other microservices. There are many different paths how you can derive value from these ML systems. So it's a very non-trivial problem how you integrate the results to other systems. And then like maybe surprisingly scaling, yes, I mean scaling of course is a problem. In many cases scaling isn't a problem. We have many medium-sized ML problems that actually like don't have like major issues with scaling. Funny thing is that like, well, I mean like as it may sound that like data science is really something fancy and like something you do in some ivory tower, the fact is that oftentimes people have problems SSHing to servers, so there's the IT problems. We have a kind of a system for doing real-time inference, which we call our hosting service. And then like we have the data questions, which are grossly underrepresented here due to the fact that we have many other channels for just helping with the data questions. But now the one thing that I want you to remember from these slides is actually not what you see, but it's what you don't see. And the interesting fact here is that like you don't see questions that, okay, so how should I like build my model, or what kind of a DNN network architecture should I use, or like how do I do feature engineering or something of that sort. And it doesn't mean that those wouldn't be important questions. And of course, those like math, science questions, of course, are important. But especially when it comes to the machine learning infrastructure, the realization was that those are the questions that data scientists oftentimes can answer by themselves. So they can maybe answer by asking their peer. And like these are the questions that they couldn't solve by themselves. And this kind of takes me to this like a holistic like a stack that like what it takes to work on these like ML workflows. And if you go from the bottom up, like what you always need is that you always need some kind of a data warehouse. So the data needs to come somewhere. You need some kind of compute resources that then like take the data and perform some computation, maybe training a model, maybe doing batch scoring, whatever. And then you need some kind of an orchestration layer that then like orchestrates all this compute. Let's say you want to do those 20,000 models. So how do you make sure that like, well, when things fail, I mean, things are retried and so forth. And then those jobs that are scheduled by the job scheduler have to be defined somehow. And that's the question of the architecture. How do I deal with that fact that I may have these dependencies between time and models and data and so forth? And now, like when you write code, there becomes a question of versioning, and not only versioning of the code itself, but also the experiments, the kind of the kind of different like models you have and the experiments you are running. And now, like software engineers have like a decent hygiene, like when it comes to using Git, but it's not so obvious what's the right pattern for using Git for data science, which is why we also wanted to kind of think about this question. And then on top of this, we have the question that, well, so how do I operate this whole thing? Let's say I have it running in production, I have versioning, I have all this good stuff. So how do I actually operate it? And then now at the very top of this stack, we start having these questions about the data science itself. How do I do feature engineering? How do I do feature transformations? And then like finally, like what's the model that I choose? What's the right way to kind of build a statistical model to represent the problem that I'm supposed to solve? And now, like what I just said, like in the previous slide, like our like a view of the world is this. Only the questions at the top of the stack are actually the ones that the data scientist cares about. That's the fun part. Like it's the topmost layer, occasionally the kind of the second topmost layer, well, seldom like the model operations, and pretty much like everything down there is something that like honestly, I haven't met a data scientist at Netflix who would say that they really have strong feelings how the data warehouse should be built, or like how to schedule Docker containers. And this kind of leads us to the realization that the issues, like kind of the questions at the top of the stacks are exactly the ones that we shouldn't worry about, which is almost like a paradox that like my title says machine learning infrastructure, and pretty much the machine learning is the only thing that I don't care about. And it's everything else. And now, like to actually make that happen, like we have been developing a package internally called Metaflow. And now a challenge, and like why we have the kind of the logo, and we even have a T-shirt and then stickers for Metaflow, is besides the fact that it's always cool to kind of come up with new projects, is the fact that we are a small team, and like we are supporting a data science organization that's about 20 times larger than our team. So like we kind of need a combination of like, well, some human support as well as then some software to provide leverage. And here, like kind of the gradient shows that like we are actually like the package itself wants to be quite kind of opinionated in a way about the lower levels of the stack. We want to help people like getting data. We want to help people orchestrate their code, deploy to production, stuff like that. And we are becoming increasingly less opinionated about the top of the stack. And the reason for that is that, well, not only like the data scientists care about those things and that's in their domain of expertise, but also the fact that if we tried to be super opinionated about the model development, no one would be using the package because they would say that like, no way, I mean, I want to do things my way. So, but I mean, this seems to be working pretty well. And now, I mean, I just want to give you a quick taste, like what it actually looks like. So this is kind of a table stake. So probably most of you here like might know Python, and like we kind of model like our like view of the world is such that well you get some input data, you do some compute, and like you produce some output data. That's simple enough. And now like the next question is that, okay, so how do you structure that like a big like a circle in the middle? Like what's the kind of the structure of the code? And what we like realized is that like as with many other data science packages out there, it's kind of quite natural to model your data science project as a DAG, as a directed acyclic graph. And one thing that like we are quite opinionated about, since we want to be somewhat opinionated about how to structure the code, how to do the architecture, is that there's no separation between like configuration and the code. But I mean the DAG itself is embedded there in the code. So you can see that like we have the nodes of the graph as these like methods in the code decorated with the step. And then we have the edges of the graph with the self.next transitions. So that piece of code like fully defines the graph on the left-hand side. And now you can get the DAG. So I mean, nothing too special about that. Well, things get a bit more interesting like when we get to the question, for instance, about dependencies. So always in these machine learning projects, there's the question that, okay, so how do I deal with these machine learning libraries? And now, in this case, like for instance, like let's say that like in the step A, I want to use one version of TensorFlow. In the step B, I want to use another version of TensorFlow. Maybe I want to compare two different versions. So now what we do is that we allow you to define like quite simply just the versions of libraries that you want. And when you execute this piece of code, the system automatically gives you this isolated execution environment. So you get exactly the version of the TensorFlow that you need, and like exactly the same version of like the environment that like you need to execute the piece of code. And not only like this allows you to specify like exactly the libraries and make sure that like you don't get these like effects with something like fancy impute chaining behind your back, but also, I mean, this makes things decently reproducible because we actually store the exact code that you are executing. We store the execution environment, and we also snapshot the data that's going in. So now when you want to reproduce not only your results, but let's say results by someone else, you can like rather easily do it. I mentioned about data access. This is like somehow like a big like a passion of mine. As I mentioned, like you can definitely use something like a Spark or Presto to access the data. You can use SQL. I mean, as I mentioned, that oftentimes ends up being the bottleneck. So what we did is that like, since our data warehouse lives in Amazon S3, we developed a client. And I have multiple times asked that AWS should do this for all. So I mean, not everybody would have to reinvent this wheel, but there's a way to make sure that you can saturate the throughput between S3 and EC2 instances if you are using AWS. And like you unfortunately can't do it using the default AWS CLI, the client. But I mean, by doing that, like what we can do is that we can get the full large data sets, which in our case oftentimes encoded as Parquet files, to a machine learning workflows like really, really fast. And in this case, like let's say you can have a big box which gives you like up to 20 gigabits per second throughput. So this allows you to kind of like get the data fast so you can iterate on the projects like faster than before. So this is like one feature that like the data scientists, maybe like even the most of all the things that we have provided this far, because this makes life so much faster that you never have to wait for data. Another big thing that I mentioned was about scalability. Now there are like two ways like how we deal with scalability. So the first one is that this is maybe kind of a bit like unorthodox, but actually we want to avoid you from doing anything fancy when it comes to scalability as much as possible. So there are many distributed frameworks out there. By the way, we use Spark for ETL and so forth. But what we have also noticed is that like if you can avoid doing anything fancy and distributed, you should totally do it. And you should really like try to kind of keep things in a non-distributed manner as long as you can. At some point, I mean, you can't anymore, but I mean, it's actually surprising like what you can do these days with just big boxes. So we make it very easy for you to kind of go with the vertical scalability, which means that like you can request, let's say, a box with 16 cores, like in this case for the step A, or you can request a box with 200 gigabytes of RAM. And you can imagine that like if you had a efficient enough way to represent your data in memory, you can actually fit all like Netflix accounts, like 100 million accounts with a decent number of features just in memory on a big box. So you should really do the math, and it's kind of surprising how much you can do on a single big box. Well, now, as I mentioned in an earlier example, if you want to train 200,000 models, you definitely don't want to do it even in a big box. But what you want to do instead is that like you want to distribute it over like a number of parallel tasks. So there is a simple syntax what we provide for just like defining a list or a grid. And then like you can fan out like everything in this grid to basically a container management system. So you could imagine like doing something like this on Kubernetes. So we have a different system, but I mean the principle is the same. Funnily enough, there was a data scientist who mentioned that like, yeah, I mean like fanning out is like easy enough. You could do this on a command line using something like xargs and many other ways. But actually fanning in is hard. So kind of just like a distributing work is easy enough, like getting the results back is hard. So, but I mean, like we provide also like an easy enough way to get the results back as well. And this way you can now imagine that like you could just like have a list of like 200,000 models or something of that nature. And then like kind of farm it out to a like compute cluster and like get everything done in a reasonable time. I mentioned about versioning. I mean, not the favorite topic of many people. I mean, still like quite important because it is not the like favorite topic of almost anyone. So what we do is that we kind of just take care of it behind the scenes. You don't have to do anything. You don't have to use Git. What we do is that we snapshot the code. We also snapshot the internal state, as I mentioned, and like we just keep record of absolutely everything. And this is like another kind of a take-home message for you that like when people try to decide like what to persist. And there are actually many machine learning frameworks, machine learning infrastructure frameworks out there that allow you to persist or allow you to kind of record some artifacts. And oftentimes people are quite conservative what they do, like for the reason that they are afraid that they might like kind of consume too much space or something of that sort. We did the math, and actually data scientists are way more expensive than Amazon S3. So like, it totally makes sense to kind of just like persist pretty much nearly everything, which is what we do, and then like we give things IDs, and like you can even tag things. And then like what's a really cool thing about this is that this kind of relates to the next point that I wanted to mention, which is about model operations and monitoring, which is the question that, okay, so now how do you know if things work or not? It would be tempting to create a UI, one UI to rule them all. And we realized that's pretty much impossible. So instead of like having a magical UI, we let data scientists to define Jupyter notebooks where they can access any point in the internal state of these workflows. And then like they can use whatever visualization packages they want to then like visualize the state of the model. And why this is important is that there isn't a single measure that works for all models. In some cases, you are interested in like a RMSE, or in some other cases, there's something else that really makes a difference. So we let it be model specific, but we make it very easy to access like everything about the kind of the status of your pipeline. So now, okay, so this was just like a quick taste, like what we have built. It is really a combination of the code plus the fact that like we are generally like speaking quite friendly people that has made Metaflow like decently successful at Netflix. So overall, like since we started like around like the first release was like early 2018, and now we are at 600 projects like running on the system. And well, one caveat here is that it's not like a 600 machine learning projects like running in production, but it's rather 600 projects at different levels of maturity. Some of them are like at very early stages. People are prototyping. Some of them are absolutely business critical, controlling like $10 billion spent every year, which is kind of scary. But I mean, the important thing is that we actually like fully embrace the fact that all these data science projects are experiments. Like not all of them are supposed to even succeed. What we want to do is that we want to fail fast. And that like brings me to the kind of the last point, which is kind of the most important thing, is that it used to be so that like when we went about creating these projects, it usually started by data scientists like prototyping something in a Jupyter notebook. And then like they presented the results maybe to their manager or like a PM or someone else showing that, oh, this thing really shows promise. And then they maybe decide that, okay, so we should really invest in making this a proper thing. And then there's maybe a data engineer involved and a software engineer, ML engineer involved and so forth. And then maybe after a quarter, I mean, they deploy it to production. And then when it's in production, they notice that it actually doesn't work as well as they expected. And like all that work, like throughout the quarter with all these people was wasted. And like usually that happens only when you kind of connect your ML pipeline to a kind of a real world systems like upstream and downstream, that you notice that actually it really doesn't work as well as you expected. And that would be fine. I mean, there's nothing wrong with that. I mean, that is totally expected. But the only problem is that like you have to fail fast. You want to kind of get to that point as fast as possible. And that's why the fact that like now about, I don't know, like in total, maybe like a 30–40% of the projects like kind of deploy something to this like a real world, like kind of a production like setting in about a week or a few weeks. It's really great because this allows us to kind of start evaluating as early as possible that like what are those real issues that will only like kind of pop up when running in production. And that's really important. So I guess that's all I had today. If you are interested in giving Metaflow a try in your organization, like please contact me. Okay, thanks. Okay. Questions? Do we have time? Okay. Thanks.
It's a great talk. So in the middle of the presentation, you mentioned that you snapshot everything and including data.
Yeah.
So I really copy the original data who trained the model. So that could be pretty big.
Right. So yes, I mean, there are like some caveats to that, like, and especially when it comes to the original source data, like that's something that like we are actively developing, how we could like snapshot like that even more actively. So no, I mean, we are not like snapshotting absolutely everything. For instance, like we are also like starting to do more things related to computer vision. We are not like taking a copy of like every single frame of Stranger Things. I mean, just for this purpose, but pretty much like everything else that happens inside those pipelines. And there's like a lot of internal state that get snapshots. So.
Okay, I got a second question. I saw this presentation by one of your team managers, and I know you're internally using a different container to run up these instance. But she also mentioned that you can also replace that with Kubernetes. Have you worked on that?
Yeah, that's actually something that we're actively working on right now. So we have, I mean, maybe you are referring to Tidus, which is an open source container management system developed by Netflix, which is what we use internally. But I mean, it's very similar to Kubernetes.
Okay, great. Thank you.
So in your talk, you didn't talk about data provenance. Like, do you provide any support for that for, when you find a bug in X and it's downstream carried through, how you clean up?
Yes. Great question. I would love to say something more about that. It is something that like we care about, and like we have actually features in the data platform to support with that. I would be lying if I said that like we are doing really good job with that. So, but yes, it's an important point, and like we are working towards making it better.
Another question. Oh, sorry. Are you trying to assign a dollar value impact upfront? Like you mentioned, like $10 billion. Yeah. When you embark on something that is going to take longer than a few days, maybe a quarter to deploy with many resources, you make a decision like, okay, we're going to put like dozens of folks on it, and because it impacts $1 billion.
Yeah, good question. The answer is confidently no. And I think, I mean, like really the reason why we don't do it is that it's just so hard. So how would you know? And the whole point is like by making these iterations fast enough is to try to kind of create data points and like increase confidence about the system before we have to make those hard judgment calls. So at some point, yes, I mean, it might be that like we have to make a bigger investment, and then it's more important to actually make that. But I mean, like making it upfront, I mean, it would be very hard. So.
Hey, great talk.
Thanks.
You spoke a little bit about ML ops and tracking the pipelines, for example, maybe for drift or maybe for, hey, everything looks different. I don't know what happened in my pipeline. Could you elaborate a little bit more on the tools you provided your team for that?
Yeah. So now, like the challenge for us is, again, I mean, going back to my point about like us supporting so many different use cases that like we really haven't found. I mean, maybe we are not just like smart enough, but we haven't found a way to have like a really good like a generic approach to kind of solve these questions. The overall mindset that we have is that like model operations is such an important part of each individual project that like as you are developing the software and as you are developing the model, you should also think about the operations and what are the things that you should be monitoring. And then we provide tools like the notebooks. And by the way, I mean, like we have plenty of like infrastructure around notebooks, so you can automatically like render these notebooks, you can schedule notebooks and like so forth. So then like the data scientist in the cases where it really makes a big difference can like then use various libraries and like techniques, whatever like works best for them to kind of define these things in notebooks and basically use notebooks almost as kind of like a UI for these things. But no, I mean, unfortunately, like we don't have any kind of like a magic bullet solution to the questions.
Okay. And are you going to open source any of that?
Well, I mean, like not the stuff that doesn't exist, but yes, I mean, we are considering open sourcing Metaflow, yeah. Yeah.
Great, thank you for the talk. Very relatable. A question that I had is, you touched on this a little bit, but I was wondering if you could outline a little bit more. What are the prerequisites for using Metaflow in terms of, you know, I heard the data needs to be in Parquet format, and you know, are you wed to AWS, or could somebody come in with a different cloud platform, or maybe on-prem? Can you just elaborate a little bit more on the requirements? Thank you.
Yeah. Well, yeah. There are very few hard requirements. I mean, one thing that we do feel quite strongly about is this idea of a cloud, in the sense that like we very much like rely on like elastic compute and like elastic storage. Like the fact that like we are snapshotting everything. By the way, we are like using S3 as a kind of a content at rest storage, so we do deep duping. But I mean, we are based on the assumption that like the storage is more or less infinite. So if you can do that on-prem, I mean, good for you. Like, but it would be hard. And the same thing with compute. That like when you're doing this like a fan outs or like requesting like a big boxes, again, I mean, having some kind of a cloud would be helpful. Netflix has been like using AWS for the longest time. Technically, there's absolutely no reason why the same couldn't work on Google or Azure. It just happens to be so that like we have used AWS. But I mean, besides that, I mean, even the Parquet isn't the hard requirement. It just so happens that most of our data sets are in Parquet today. Yeah. Cool. Thanks.